All right, so now we're going to work through an example that kind of hits the high points of what we just talked about, almost all of them. So we're going to be talking here about methylamine, which is a weak base, and at 25 degrees Celsius, its Kb is 4.4 times 10 to the negative fourth, lots of fours. All right, so here's our three-part problem, 3 parts with part 3 having 3 parts to it. We're going to write the chemical equation for the reaction that corresponds to Kb for methylamine. We're going to figure out, excuse me, what the standard delta G is, and we're going to figure out what delta G is under these particular conditions that are decidedly not standard conditions. And don't worry, I'll rewrite these as we go from slide to slide. So let's tackle the first one and the second one in the next slide. All right, so first off, what's the chemical equation? So this is something you should be able to do. Looks like y'all did a pretty good job of it on the exam. So, you know, it's again methylamine plus water. It's going to take a proton away from water and become methylammonium, CH3NH3 plus, and leaving a hydroxide from the water. So that's Kb. So what's the standard delta G? Now, the easiest way, remember that we did talk about a few different ways of calculating the standard delta G for a particular process. Now you could go look up delta G's of formation for methylamine, methylammonium, and hydroxide in liquid water if you could find them. But in this case, the easier way to go about it is just this relationship right here, that standard delta G is equal to negative RT natural log of K. And you've got all that information, you can just plug it in. Don't forget that this is the joules per mole per Kelvin version of R, so you've got 8.314, temperature is 298 Kelvin, and then times the natural log of just 4.4 times 10 to the negative 4. And that, when you do this, will actually give you an answer of, you know, positive 19,100 joules or thereabout. Don't forget, be careful with units. So there's a joule buried in here. Typically, these things are converted to kilojoules per mole because that's a more manageable number. So in this case, it is positive 19.1 kilojoules per mole. What does that mean? That means that this is reacting under those conditions. It is reacting spontaneously in the reverse direction. So if you start, remember what that standard conditions mean. It means that this is 1 molar, that's 1 molar, and that's 1 molar, and we'll get pure water here. So under those, at the instant that these concentrations are all 1 molar, that means the reaction is going to be reacting in reverse direction. So you'll be forming more methylamine and reacting away some of the hydroxide and methylammonium. All right, so those are the first two, pretty quick. Now let's figure out what the delta G is under those very specific conditions that I gave, which were these right here. And so we've got 1 molar, we've got 6.7 times 10 to the negative 9 molar hydronium or H plus. So again, this is going to be this is under basic conditions. We have 2.4 times 10 to the negative 3 molar methylammonium, and then finally 0.098 molar of the methylamine. So you will note that in this case, these are decidedly not standard conditions. So we're going to need to use the relationship between the standard delta G and Q, which we now know. But the first thing that you might have spotted is that I didn't tell you what the hydroxide concentration is, but keep in mind, I did tell you what the hydronium concentration is, and never ever forget, those two are related. And they are related thusly. The hydroxide concentration is going to be equal to Kw divided by the hydronium concentration, or the H plus concentration. So with an extra sig fig here, we're talking about 1.49 times 10 to the minus 6 molar. So we make sure we do that. And from there on in, you can plug and chug into the Q for this equation. So Q is going to be equal to the methylammonium concentration times hydroxide concentration divided by the methylamine concentration. If you plug in all the numbers that we've got here, you should get, again with an extra sig fig, about 3.67 times 10 to the negative 8th. And then to get the delta G under those exact conditions, just remember this relationship right here. We got this from the previous part of the problem, so that is this positive 19.1 kilojoules per mole. And then just evaluate this, and don't forget, and this is a common goof, that as it is written in here, this is actually going to end up being in joules. And this here is in kilojoules, so make sure that you convert this to kilojoules is probably the way to do it. And what you get is an answer that is negative 23.3 kilojoules per mole. So note that in this case, the direction of the spontaneous change actually flipped, and that under those conditions, this reaction will be reacting spontaneously in the forward direction. All right. All right, so here's another example. So we'll be looking at the decomposition of ammonia to form molecular nitrogen and molecular hydrogen. And we're going to, in the end, figure out what the delta G is going to be given these amounts of ammonia and hydrogen in a container, along with 0.306 moles of ammonia in that container as well. So this one, these are all gases, so we're just going to go ahead and use the pressure-based reaction quotient for that. So the relationship that you would want to use right away would be that the delta G under non-standard conditions would be equal to delta G under standard conditions plus the quantity RT times the natural log of Q. Problem is that to start with, you don't know this. So one thing you could do, let's say, is go to the appendix of your book, whether it's the electronic or the real version, and note that the standard delta G of any reaction, we talked about this before, is equal to the sum of the free energies of formation of all the products times their coefficients minus the sum of all the free energies of formation of all the reactants times their coefficients in the equation. And these are tabulated. And so you could do that, let's say, and look them up, and what you'd find is this actually is not particularly difficult, because you will find that for the products, they're both 0 kilojoules per mole because they are elements in their preferred state. So the free energies of formations have exactly the same definition. They correspond to the same reactions that the enthalpies of formation do, and for exactly the same reasons, the free energies of formation of elements in the preferred state, like our friends N2 and H2 here, are by definition 0. I will note the same does not apply for entropies. I repeat, the same does not apply for standard entropies of elements in their standard states. Those are non-zero. So the only non-zero term here would be that for the ammonia. So here you're going to have a negative, or you're going to subtract 2 times negative 16.5 kilojoules per mole. This is for the ammonia. And just be real careful with the sign propagation here, and this ends up being equal to positive 33.0 kilojoules per mole. All right, so now we've got the standard delta G of reaction. Now we can work on the standard delta G's under these given non-standard conditions here, and that actually I have nice and pretty for you. So the first thing we need to do actually is remember that so in this case, the pressure-based reaction quotient is going to be equal to the partial pressure of H2 cubed times the partial pressure of N2 to the first power divided by the partial pressure of NH3 squared. And so what we need to do is actually figure out these partial pressures. Remember, I just gave you amounts. So this is a good Dalton's law reminder. And for that, we'll go to the next slide. So the partial pressure of H2 and N2 are going to be the same because they have the same amounts. And so plug in again, make sure you use the right version of R. So that corresponds to 0.02 atmospheres of each of those guys. Work out the same calculation for the partial pressure of the ammonia, and that turns out to be about 1.5 atmospheres. And now that we have that, we can calculate the pressure-based reaction quotient QP, plug in the numbers to our formula, and that gives us about 7.1 times 10 to the negative 8. And last but not least, now we can plug into the equation that would give us the delta G from the standard delta G's and the reaction quotient adjustment. Again, be careful with the R units. So here I converted this back to joules, so negative 33 times 10 to the third joules. And then this ends up being negative by about 7780 joules, or negative 7.78 kilojoules. So again, under these conditions, the direction of spontaneity was actually different than it was under standard conditions. And that happens a lot.